Assalamualaikum students, welcome to Electronics. I am Madam Rosmina Azwin Abdul Rahim. So as usual, let's go through this one hadith. Ka'b ibn Malik reported the Prophet ﷺ said, whoever seeks knowledge to impress the scholars, to argue with the foolish or to attract the attention of people, Allah will admit him into hellfire. Source Sunan Al-Tirmizi. So I'm sharing this hadith with you to remind you guys, students, please be careful with your intention. Always set your intention for the sake of Allah, lillahi ta'ala, because by seeking knowledge, if we have the correct intention, inshallah, that will cause us to enter paradise. Okay, now we come to chapter 3, which is on diode circuits. This video covers chapter 3a, which has 3 subtopics. The first one is introduction to rectifier and half-wave rectifier, as well as rectifier parameters. Okay, now we come to the first subtopic, which is introduction to rectifier. So as you know, in order for us to function our electronic circuits, we need to have DC power supply, especially for active components, remember? So in our case, the power coming to us normally comes in the form of AC. Okay, so we have to convert this power from AC to DC so that we can use this power supply to function our electronic circuits. Okay, so that's why in this building block for electronic power supply, okay, as you can see here, the signal coming from AC line normally comes in the forms of AC. Okay, then it will go through the diode rectifier here. Okay, so as you can see here, after it goes through diode rectifier, the signal initially in the form of sinusoidal wave, now it becomes still sinusoidal, still AC, but it is now limited to one polarity. Then if we go further, the signal is being connected to a filter. Then as you can see here, we can have some sort of ripple signal. Okay, then if it goes through the voltage regulator here, in this case, now only we can get a straight line representing DC power supply. Okay, then only it can be connected to our electronic circuits. Okay, what I want to highlight here is this box, which is the diode rectifier. Okay, so basically rectification is the process of converting AC to one that is limited to one polarity. So as you can see from here, it will convert the sinusoidal wave to still sinusoidal, still AC, but limited to one polarity. Okay, then rectification can be classified as into two types, which are half wave and full wave rectifiers. Okay, before we go further to second subtopic, I would like to highlight one thing to you. Remember before this, we talked about diode AC analysis and DC analysis, right? Okay, for diode DC analysis, we can consider the three models, remember? And last time when we consider AC analysis, we represent the diode with a resistor RD, right? Okay, this is for AC analysis. But you should take note that for this AC analysis, normally the signal, the AC signal is in the form of low voltage in the range of millivolt. Okay, then only we can do this representation of diode modeling, where diode can be replaced with a resistor RD. When we deal with AC signal, a small AC signal in the range of millivolt. Okay, now coming to second subtopic, which is on half wave rectifier. So as you know here, the signal still we talk about AC signal, sinusoidal wave signal. Okay, AC signal. But in this case, since this AC signal is normally in the range of volt, I mean, it is much higher, okay, compared to the one that we discussed before in millivolt range here. In this case, what we are going to do is basically, although we are talking about AC signal, but the diode representation for half wave rectifier as well as full wave rectifier is similar to the one in DC analysis. Meaning to say, for example, you have this AC signal of sinusoidal wave, right? Where you have positive half cycle and negative half cycle. So in this case, what you are going to do for half wave rectifier as well as full wave rectifier, we are going to consider cycle by cycle. Meaning to say, let's say we consider for the positive half cycle, we talk about positive voltage. So our Vs is represented by positive and negative like this. Okay, so by doing so, we can see that this Vs positive one is connected to positive terminal of the diode, while the negative one is connected to the negative terminal of the diode, meaning at this time the diode is under forward bias. Okay, then when we consider for the second half, okay, which is the negative half cycle here, okay, then we are dealing with negative voltage, right? So in this case, this Vs is being represented with negative and positive. Okay, now Vs is being represented with negative and positive like this. So under this condition, negative is connected to positive terminal, positive Vs is connected to negative terminal. So we know under this condition the diode is off, open circuit, there won't be any current flow. Okay, what I want to highlight here is in rectifier, because we deal with relatively higher voltage of AC, so the analysis is similar to the DC, where the diode can be replaced with the three models. Okay, if we talk for the first model, it's either, remember, either diode, where when the diode is on there will be short circuit. If we consider for the second model, remember, it can be replaced with V gamma. If we consider for the third model, it can be replaced with gamma as well as the RF in series to it. Okay, you can see here it is actually a basic half-wave rectifier circuit. Okay, then this rectifier circuit normally comes together with this step-down transformer. Okay, so as you can see from here, we have Vi, the input voltage, which is connected to the step-down transformer with a ratio of N1 and N2, and later the step-down voltage is given by Vs. Okay, so the voltage that is being involved in our diode circuit analysis actually Vs, okay, which is connected to the diode, and later it is connected to R. Okay, you can see one closed loop here, right? Okay, then one thing that I need to highlight here, if in the case that you are given the Vi value and the transformer turns ratio is given, okay, so you can first find for this Vs. Okay, for example, Vi is given by um, Vi over Vs equals to N1 over N2. Meaning to say, if the transformer turns ratio is given, Vi is given, we can find for Vs. And take note, this Vs is being used in our diode analysis. But in the case that Vs is straight away given, okay, so you don't have to do this part. You can straight away use the Vs value that is given in the example. Okay, then coming to the diode analysis. Okay, as I mentioned to you before, normally for rectifier case, we consider cycle by cycle. Okay, so let's have a look for the first half cycle, where we have the positive voltage here, right? So in this case, Vs can be represented with positive and negative like this, meaning to say the positive is connected to positive terminal, the negative is somehow connected to negative terminal. So in this case, diode is forward bias. Okay, but you should take note that although the diode is forward bias, but initially when the voltage is less than V gamma, when the voltage is less than V gamma, at that time the diode is still off. Okay, the diode is still off because it is not enough, the voltage, it is not enough, remember, to overcome the barrier. So when the diode is off, open circuit, no current flow, obviously, then at that time V naught equals to 0 volt. Where is V naught? V naught is the voltage which is across the R. Okay, so since the current is 0, okay, so obviously the V naught also will be 0. Okay, then in the case when Vs is larger than V gamma, which is, we are talking about this portion, okay, where Vs is now larger than V gamma, only at that time the diode will be on, the diode will conduct, then obviously there will be current flow. Okay, then how do we do the analysis on this? For this one, because we are having one complete loop, one closed loop, we can get KVL equation, right? So the KVL equation is given by minus Vs plus Vd plus V naught equals 0. So in this case, our V naught is actually Vs minus Vd. Okay, so Vd is the voltage across the diode. So it depends. If we talk about the first model for the ideal diode, Vd is 0. Okay, if we talk about the second model, the Vd will be equals to V gamma. And if we talk about the third model, Vd should be equals to V gamma plus ID RF. Okay, if you still remember. So in this case, as you can see from here, V naught is actually equals to Vs minus Vd. Okay, then obviously from there we can find for the diode current where V naught is actually equals to ID times R. Okay, so ID is actually V naught over R. So that's why we are getting this equation. So for the same analysis just now, we can say that whenever Vs is less than V gamma, the diode is off, no current flow. So that's why we are getting V naught equals 0 volt. Okay, so this condition when Vs is less than V gamma, it can be this portion, okay, Vs less than V gamma, and it can be also this portion, the negative half cycle, where obviously the value of Vs is less than V gamma because we are talking about negative voltage. Okay, so this condition is applicable for these two portions here of the signals, and the condition when Vs is larger than V gamma, it is this portion, okay, where obviously at that time, as you can see from the circuit just now, the diode conducts. Then that's why we're getting V naught equals Vs minus Vd. Okay, so if we were to draw the output waveform, you can see from here that whenever the V naught is Vs is less than V gamma, the V naught equals 0, right? So as you can see here, V naught equals 0. It is represented with a vertical line like this. A horizontal line like this. Okay. Then when we have Vs larger than V gamma, you can see that V naught is actually Vs minus Vd, meaning V naught is equals to Vs, but it is being reduced by how much? By Vd value. So as you can see here, okay, it is being reduced by Vd value. Okay, let's have a look on this basic half wave rectifier circuit. Okay, in this case, R is given as 1 kilo ohm. Then V gamma is given as 0.6 volt, as well as RF is given as 20 ohm, and assume Vs is 10 sine omega t. Okay, in this case, you have to determine the peak value of the diode current, and as well as you have to sketch V naught versus time t and label the peak value. Okay, in this case, first you have to identify which model are we referring to. Okay, so obviously it is the third model because V gamma and RF are given. Okay, then as you can see from here, Vs is given as 10 sine omega t, meaning we have something like this, right? Okay, Vs is, the amplitude here is 10, here as well is the negative 10. Okay, then we have the V gamma value, okay, with the value of 0.6 volt. Okay, so in this case, since we are going to determine the peak value of the diode current, then obviously we know we are going to get diode current when Vs is larger than V gamma only, right? When Vs is larger than V gamma, only the diode will be conducting, only we are going to get current. Okay, meaning to say we just have to consider only one condition where Vs is larger than V gamma. Okay, because at that time the diode is on, and when the diode is on, remember we are considering the third model, meaning to say this diode can be replaced with V gamma and a resistor RF in series to it. Okay, so in this case, our KVL equation would be, okay, remember we are considering the positive half cycle, positive Vs and negative Vs like this. So KVL equation, it will be negative Vs plus V gamma plus IDRF plus IDR equals 0. Right? This KVL equation. Okay, so if we rearrange, we are going to get ID actually equals to Vs minus V gamma over R plus RF. Okay, then in this case, we are looking for the peak of ID current, okay, peak of diode current ID. So obviously here the Vs should be at the peak as well. Okay, so in this case Vs peak is given by 10 volt, right? The amplitude of it. Okay, so we can just substitute. Vs peak is 10, V gamma is 0.6 divided by 1k plus the 20 ohm. That will give us the value of ID peak. Okay, so as can be seen from here is the same thing that we have discussed before. So if we calculate, we are going to get ID equals 9.22 milliampere. So this is the diode current, the peak value of the diode current. Okay, then for the second one, we are supposed to draw the output waveform, right? Okay, so as you can see here, this is the output waveform. Okay, so but my advice to you, always draw the output waveform together with the Vs value. Okay, so that it will be easy for you to see and compare. Okay, so as you can see from here, since ID is given as 9.22 volt, okay, so you know that V naught is actually IDR, right? So we have 9.22 milli times the 1k, so that's why we are getting V naught is 9.22 volt. So that's why the peak of output voltage is 9.22. Okay, but as you know, the V naught is being reduced by V gamma value. Okay, then that's why we have this curve, and obviously when Vs is less than V gamma, we are going to get zero current as well as zero voltage, zero output voltage. Okay, so this is the output waveform for the half wave rectifier. Okay, now we come to the third subtopic, which is on rectifier parameters. Okay, there are three things that you have to know. First, on the transformer ratio, but we have discussed this before in previous example, where transformer ratio is being given as the relationship between the number of turns ratio, okay, to the voltages. Okay, we as our Vp over Vs equals N1 over N2, remember? Okay, then we have peak inverse voltage. What is it? We call this as PIV. It is actually the peak value of voltage that a diode can withstand when it is reverse bias. Okay, so whenever you design a rectifier circuit, you always have to check the PIV value for each diode to make sure the diode is not being damaged throughout the operation. Okay, then another terms that you need to be familiar of is actually duty cycle, where duty cycle is actually the fraction of the wave cycle over which the diode is conducting. Okay, so if you know that if duty cycle is 50%, so you know that 50% of the time diode will be on and another 50% diode will be off. Okay, then this is the one that I mentioned just now for the transformer turns ratio. Whenever you come across the step down transformer, then you can simply get the relationship between the voltages and the transformer turns ratio. Okay, remember before this I mentioned about the peak inverse voltage, PIV. So sometimes it is also known as maximum reverse bias voltage. Okay, then we want to know whether our diode can withstand a certain voltage when it is reverse bias. So the reason is we want to avoid damaging the diode when it's operating. So we should know that each diode has its own PIV rating. For example, if you go to the lab, you take one diode, there will be a data sheet for that diode. So as you can see from here, oh, I can see the PIV for this particular diode with part number 1N4002. The PIV value is 100. Okay, and in terms of RMS, it is being given as 70 volt. Okay, so in order for us to calculate for the maximum reverse bias voltage, okay, for a particular diode, for example, in this half wave rectifier, so we know that the diode is reverse bias when it is at negative half cycle. Remember, negative half cycle, the diode is open circuit, no current flow, the V naught also will be zero. Remember, okay, the diode is off, open circuit. So in this case, at that time, for the negative half cycle, Vs is represented by negative and positive like this. Okay, so for the same circuit, we may represent the diode by this where we have negative Vs to indicate the reverse bias voltage, okay, sorry, to indicate the negative half cycle. And since the negative terminal of Vs is connected to the diode, okay, so the potential, the voltage across the diode, we give it as negative Vr, okay. So this is the reverse voltage across the diode. Then at that time, we know that since here it is open circuit, right, no current flow, so obviously here V naught also will be 0. Okay, so V naught also will be 0. So in this case, if we were to do the KVL, okay, we are supposed to get negative VR plus 0, which is the V naught, okay, plus Vs peak equals 0. So in this case, our VR is actually equals to Vs peak. Okay, so meaning to say, if let's say our Vs peak for previous example is 10 volt just now, okay, so we know that the reverse voltage across our diode, the maximum reverse voltage will be equals to 10 volt. Okay, so in this case, when we choose our diode, we should choose a diode with PIV rating of at least 10 volt, okay, or higher. Okay, so if we choose PIV rating of, for example, 8 volt, but in reality our diode sometimes it may experience 10 volt maximum reverse bias voltage. So at this time, the circuit is not good because maybe the diode will be damaged throughout the operation. Why? Because the PIV rating for that particular diode is just 8 volt, but in reality the diode may experience negative voltage of 10 volt when it is being reverse bias. Okay, so whenever you know the reverse bias voltage for a particular diode, so you should choose the PIV value which is about the same value with the VR, or it should be larger than that. Okay, it could be 11, 12, or 13, or 14, whatsoever. Okay, now we need to understand this concept of duty cycle. Okay, where duty cycle, as we discussed just now, is actually the fraction of the wave cycle over which the diode is conducting with respect to the full wave of the cycle. Okay, so we are considering one cycle. Okay, so for this particular example, we know that um, here at this portion, okay, no current, meaning the diode is not conducting. Okay, so you can estimate the duty cycle is actually, it should be less than 50%. Okay, why? Because obviously 50% the diode is off, not conducting when it is negative half cycle. And at the same time here also we have the condition when the diode is not conducting, okay, where Vs is less than V gamma. Also here at the same time we are also having condition when the diode is not conducting. So that's why we can estimate duty cycle for half wave rectifier is less than 50%. Okay, now let's calculate for it. So as you can see here, okay, we know that for previous example, V gamma is given by 0.6 volt, right? Okay, so we know that at this particular theta 1, obviously we want to find for theta 1 and theta 2. Okay, so at this particular theta 1, the voltage is actually given by 0.6. Okay, the point when the diode starts to conduct. Okay, remember V gamma should be larger or equal 0.6, then only the diode will be on, right? Okay, so the starting point when the diode starts to conduct is at 0.6, so that's why we have 0.6 here. 10 sine omega t. Omega t is actually refers to theta 1, the one that we are looking here. So in this case, if you rearrange this equation, you are going to get theta 1 equals to 3.44 degrees. Okay, then for this, for the second quadrant of sine wave, to represent the theta 2, okay, so it should be just 180 degrees minus theta 1. Okay, so 180 degrees minus 3.44 degrees, then you should be getting this value. So our duty cycle is given by this formula, theta 1 minus theta 2, or theta 2 minus theta 1 over 2 pi times 100%. So in this case, we know exactly the duty cycle for half wave rectifier for this particular example is 48%. Okay, here is another example of half-wave rectifier, but this particular example, I leave it to you to do your own self-revision. The final answers are given. Okay, so maybe later in class we are going to discuss this. So we come to the end of the video. So let's recall, we have three subtopics, which is the introduction to rectifier, the half-wave rectifier, as well as the rectifier parameters. Okay, students, that's all for video 3A. Thank you. Bye.